Hello everyone, welcome to the second lecture of Operating Systems Engineering. So first an announcement, make sure that you find a partner for your labs and email the TA corresponding to your lab session by by February 2nd, because that's when the lab 2 will be out, and lab 2 is supposed to be done in pairs. A brief review of the previous lecture. In the previous lecture, we have seen what operating system is, and we have seen computer from an hardware perspective. So from hardware point of view, a computer contains chipset, and which connects CPUs, processors, memory, and various input-output devices like disks, mouse, monitor, so on and so forth. So when we add software to the computer at hardware level, the software s- resides in the memory. So memory is by memory I mean main memory. So it's a non-volatile memory, and we'll be looking later what exactly we mean by memory. And then on the disk, we'll have operating system, apps, and other data stored on the disk. And in the memory, we'll have programs and corresponding data. We also have operating system software that residing in the memory. At software level, so typical operating system contains at least four independent parts. At the high level, we have applications. So this is a typical Unix operating system structure. So at the top, we have applications. So these are the applications written by programmers, and these are regular applications that we use, like calculator or paint or text editor, right? These are the user level applications, or the applications with which user interacts with. And these applications are written by programmers, and one of the important thing about these applications are usually tied to the libraries. They make heavy use of libraries provided by the operating system uh, or other vendors. Like an example of library is libc. And next is libraries. So libraries are used by applications, as I mentioned before, and these libraries are usually written by gurus. These are experts who know how to write good software, and these libraries provide an interface for applications. Basically, they abstract away all the commonly used functionalities and expose in a simple function. For instance, reading from a file involves actually doing a system call, and reading from a buffer, it involves a lot of steps. So instead of that, libc provides a simple call, or rather simple function called read. So any application now which wants to read a file can just use the library libc, and then it can just call read function inside that library. And the connection between applications and the libraries is usually resolved by a software called dynamic linker. So basically, when application makes a call to read, dynamic linker actually loads the library into the memory and transfers the control, or rather execution, to the read function, which is present in libc. So at the OS level, we have two layers. At the top, or rather on the outside, we have portable operating system layer. So this layer is an abstraction provided by the operating system. If you remember in the last lecture, uh, we and we learned that operating system provides an abstract interface. So this abstraction is provided by the portable operating system layer. Basically, it hides all the nitty-gritty details of the hardware and exposes an uniform interface through which we can interact with the operating system. And similar to libraries, these operating systems are also written by experts who know very well how to write good software, and who are experts at writing low-level code. And at the lowest most level, we have machine dependent layer. So this is the code that actually deals with the hardware. So this code um, this code is the code that interacts with the hardware. For instance, uh, input output driver. So usually these are the machine dependent code or machine dependent layer is called driver layer. So these drivers actually interact with the devices and make the devices do, basically they translate high level commands into the device specific commands. And machine dependent layer also takes care of maintaining processor and exceptions, interrupts that we'll be seeing later, and switching between operating kernel mode and user mode, and all the other stuff. It also takes care of bootstrapping, like when we turn on the computer. So the first piece of software that runs is usually called bootloader, which is actually very machine dependent because it needs to initialize the hardware and then it will load the operating system layer, so on and so forth. So another way to look at various layers of system software or various layers of software is in terms of ring. These are called, this is usually called Unix onion or Unix ring. And this actually corresponds to, if you remember x86 architecture, uh, there are privilege rings called from ring 0 to ring 1. These Unix onion roughly corresponds to those rings. Not exactly, but you can imagine the innermost layer is like the operating system layer is ring 0 and the application layer is ring 3. If you don't understand that, it's fine. So, so another way to look this various layers of system software is in terms of rings. Here at the core, we have hardware. And in order to program the hardware, there is a device driver layer, and which is again abstracted by the operating system by providing an uniform interface. And this entire thing constitutes an operating system now, which exposes an uniform interface, which is used by applications to interact with the operating system. And there is well separated boundary between applications and operating systems, and we'll be looking at this separation later in the lecture. So in this lecture, we'll go through various operating system components. Basically, these are the components that we'll be learning deeply in this course. And then we'll be looking at system calls and what is the requirement of system calls and how system calls are done in Unix. And then we'll conclude the lecture by looking at interrupts and how interrupt processing happens in on x86 machines, or rather Unix machines. So the operating system components. So operating system has many components. Depending on the design, it can have various other components. However, there are certain set of components which are static. By static, I mean these are the things that operating system has to take care, irrespective of the utility of the operating system. For instance, you can imagine these components to be present in both mobile operating systems such as Android and also desktop operating systems such as Linux or Windows. So in this course, we'll be looking at 6 components: process management, main memory management, file and storage management, input output system management, networking, and command interpreter system. So process management. First, let's try to understand what we mean by a process. So process is a program in execution. So program is just a piece of code. So program contains just bits. However, when the program runs or when these bits are interpreted by the processor, that's when we call uh, it a process. So process is basically an active form of a program. So a processor, in order to be active, it needs CPU because it needs to execute instructions that are defined by the program. And process may also need memory in order to store data. Process may also need files because it may need to read and write some files from the disk. And it also have to interact with IO devices. If process has to take input from user, then it has to interact with the mouse or keyboard or even monitor because it needs to display some text or some graphical user interface to the user. So in order to manage process, operating system has to do has to take care of managing these processes. And so process has to start. So process creation has to be taken care by operating system. Similarly, process deletion also. Furthermore, in case of time sharing systems, as we mentioned in the previous lecture, processes usually switch. Like processes are given a fixed times slot. So after the allocated time slot is expired, the processes are switched. Now operating system has to take care of suspending a process and then resuming a process later when the time slot is available. And also, operating system usually provides a form of communication mechanism so that different processes can communicate with each other. And also, in order to provide communication, it also needs to have synchronization mechanism so that multiple processes can have a mechanism to synchronize so that they can work together in parallel. The second component is main memory management. So, what is main memory? So, by memory, we mean by RAM. So, RAM is random access memory. So, and it's also called main memory. So, here, main memory is a volatile memory. By volatile, I mean the contents of the memory will be lost when you turn off the device. And the main memory is shared by different processes, and it's shared by CPU and also IO devices, and it's also shared by multiple processes. In order to manage the memory, operating system needs to, since main memory is a resource, operating system now needs to take care of allocating and freeing memory space as needed by different processes. It also needs to keep track of which parts of memory are currently used and which parts are not used. And if it is used, it needs to know which process is using that memory so that it can reclaim that memory when that corresponding process dies or it terminates. It also needs to protect the memory so that a process cannot uh, interfere with the execution of other process, because in case of time sharing systems, we have multiple processes residing in the memory at the same time. So operating system has to make sure that the memory that belongs to one process is cannot be interfered with the memory that belongs to the other process. And furthermore, operating system can also give an illusion of a bigger memory space than that is available, than that is physically available. For instance, on 32-bit machine, the virtual address space is 4 gigabytes. However, 32-bit machine can run on hardware that has 1 gigabit of RAM or 1 gigabit of physical RAM. So uh, this illusion is actually provided by the operating system, and it is part of main memory management. And the other component is storage system management. So as I mentioned before, main memory is volatile. That means when we turn off the device, the contents of the main memory is gone. So in order to have persistent memory, operating system maintains storage system. Storage system is usually disk like magnetic tapes or SSDs, and this is non-volatile memory, which actually the memory written to the disks or SSDs will actually remain between power cycles. And operating system is responsible for allocating and freeing disk space. It also uh, is responsible for scheduling disk writes, because disk writes are hardware interactions. So operating system should be smart enough in scheduling these disk writes. And the way the way like storage system is managed by the operating system is through files. So a file is an illusion given by the operating system to the user or to the applications. It's basically a unit of data that can be stored on a storage system. So OS is responsible for file creation, deletion, and it takes care of actually mapping the file abstraction into the hardware abstraction. By that I mean, so it actually takes care of saving the file into different disks or different platters of the magnetic disk. And operating system is also responsible for providing various primitives for manipulating files and directories, right? Like operating system provides facilities to list all the files in a directory. It provides it provides system calls to actually create directories, and it also has protection mechanisms. Basically, we can have permissions on the files so that we can restrict which processes can access files or not. So now let's look at IO system management. So we actually went through process management, main memory management, and file and storage management. Now let's look into the bottom three components, which is IO system management, networking, and command interpreters. So IO system management, similar to storage management, IO subsystem is also a critical part of operating system, and there are many input-output devices, right? We have mouse and keyboard to start with, and there is also monitor. And now actually we are getting fancy input-output systems such as VR controller, and we have camera, motion detector, we have various sensors. So these are all part of input-output subsystem. And the way operating system manages these variety of input output devices is by having an abstraction called input output subsystem, which actually provides an uniform interface to deal with various IO devices. And the way it does is it usually maintains a buffer so that the the devices which are providing more input can be buffered and later used by the applications. And the other component is networking. So networking, by networking, so we have so a collection of machines is a network. That's the basic definition of a network, right? And in order to ensure that these collection of machines communicate with each other, operating system has to provide a mechanism so that each machine can be able to send and receive messages from different machines. And it also needs to make sure that the communication is reliable and the communication is consistent. That means when we send the data, the same data is received at the other end. And this is very important component in modern systems, because most of the systems now are cloud based systems, and data centers use multiple machines as part of their distributed system, and banking, everything is part of everything requires network. So networking is actually a very crucial part of operating system uh, in modern systems. And finally, we have command interpreter system. So command interpreter system is actually the interface between user and operating system. Basically, this is the way in which anybody or user interacts with the operating system. So the way command interpreter system works is there are predefined set of commands that operating system can understand, and these commands, whenever user provides these commands, an operating system will perform the corresponding operation. For instance, ls is a command which actually lists files in the current directory. Cat is a command which actually reads the content of the files and displays it to the terminal. Similarly, there are commands such as ssh and scp, which takes care of networking. Basic ssh is secure shell. So we use SSH to log in on to, for instance, ECN grid machines. And so this is part of command interpreter system, and usually we call we call this command interpreter system shell. So and there are many forms of shell. For instance, on Linux we have fish shell and bash shell, and we have T shell. We have many shells. Basically, these different shells differ by the commands that they provide. And And along with command line or like command interpreter system, operating system can also provide user interface such as in Windows or Mac, which actually instead of um, providing commands, now you can actually use mouse clicks to interact with the operating system. So for the rest of the course, we'll be dealing with uh, these individual components. We'll be going through each of these components at, in depth, and we'll be looking at various ways in which these management tasks can be done. For instance, we'll be looking at various methods to manage processes and various methods to manage memory, file system, so on and so forth. And will be looking at hardware support or basically hardware layer of operating system. But that also depends on the time and when it is relevant, we may actually delve into a few hardware details of how certain management task is done by the operating system. And will also be our labs corresponds to these components. Like for instance, lab 2 will be looking at process management, lab 3 will be looking at memory management, and lab 5 will actually be implementing a file system of our own. So in each of the components, when we study, we usually see there is a common theme in these components. First, we'll be looking at functionality. First, we'll be looking at how a certain management task is done by the operating system. And then we'll be looking at performance improvements. Basically, we know what should be done. And then we'll look at how fast can we do it? How efficiently can we do it? And we'll also be looking at different trade-offs between functionality and performance. We'll also be looking at um, various solutions based on how the corresponding functionality or corresponding management component is implemented in the operating system. Like, is it implemented in completely in software, or is it supported by hardware, or is it a hybrid solution where some part is implemented by the hardware and some part is implemented by the software? So these are the common themes in each of the components. When we study each of the components, we usually see a theme which corresponds to functionality and then performance, different trade-offs. And when we look into the implementation, we'll be looking at some implementations which are completely software, some implementations which are completely hardware, some that use hybrid solutions. So now let's look at system calls. So if you remember in lecture 1, we said that operating system has two main tasks. One is being a resource manager, and the second one is providing an abstraction away from the hardware. So in order to manage resources, so it needs to be able to allocate resource and reclaim resources, right? So to do it, operating system needs to have higher privilege. So that means operating system needs to have more power than the regular programs. So in order to allow this, hardware usually, for instance, x86 provides different privilege levels. So there is a privilege level called ring 0. So in that privilege level is where the operating system runs. So basically, when the operating system runs, there is a bit set in the processor that says that whatever code that is running in the processor has higher privilege. Similarly, the code that is part of user applications, it runs in non-privileged mode. Basically, again, this is again a bit in the processor that will be unset, so that uh, when the whatever programs are running, when that bit is unset, the program can do only limited tasks. That means it's not privileged. So, so, so operating system, in order to run operating system, processor needs to have at least uh, dual mode of operation, where you have a privileged mode where all the operating system code can run. You have a non-privileged mode where the user code is can be run. So if you look at an operating system structure, uh, here we have user level. So so when we say all the software that belongs to the user level runs in non-privileged mode, and all the software that's part of kernel level or operating system runs in privileged mode. So OS needs to manage resources. However, we should have a way in which user requests the resources, right? Because in order to manage the resources, OS needs to know what process needs what resource and what process doesn't need some resource, right? So there should be a mechanism uh, for communication between user mode applications or user mode code and the kernel mode code. This is done by system calls. So system calls provide a mechanism to communicate uh, from user space to the kernel space and vice versa. So, so kernel manages shared resources, and system calls provides a way in which applications can request access to these resources. And these system calls are usually done by writing small piece of assembly code. However, you can invoke system calls in various languages like C, C++, Perl. You can actually invoke language like system calls in Python as well. So, but system calls needs to be done in assembly. So how can we do this in different languages? Answer is libraries. So these libraries actually encapsulate these assembly instructions, and uh, they provide like language specific layer. For instance, you can see that various Python modules at the lowest level they're actually using assembly, whereas we just call Python code at the end, and which is actually provided by libraries. So these system calls are actually encapsulated by libraries. That's why we never see when we are writing an application, we rarely write system calls. We just use library functions. An example is open, read, write, and close. If you have taken data structure course or advanced C programming course, you remember that in order to open a file, we need to call open function from libc. So, however, open function actually what it does is it actually does a and system call to the operating system to open a file. However, this is all encapsulated by the libraries. So all we need to do is just call open function. That's why we don't see direct invocation of system calls in most of the programs we write. So there are various categories of system calls corresponding to the different components of operating system. Like there are various system calls that has to deal with process management, memory management, file management, device management, and networking. So depending on the uh, task, or rather depending on the resource that we want, the system calls belong to corresponding categories. So if you look at the man page of Linux, you see the various system calls that are supported by Linux. And the way system call can be done in C, you can actually just use the number. So each system call has a number. So you specify the number of corresponding to the system call that we want to invoke along with various arguments for the system call. For instance, if we want to uh, open a file, then we would use the corresponding system call number along with the file name as one of the arguments. So this is an example of uh, a system call invocation where system call is actually getting the process ID of the program of the process. So this is actually lab one. Like if you haven't looked at lab one, when you look at lab one, you will see that lab one is actually implementing the system call. And how does system call gets executed? So when user process makes a system call uh, through an assembly instruction, so there is a trap happens. By trap, I mean it's an interrupt that happens in the processor, and then processor transfers the control to the operating system. Operating system now knows from the arguments that are given to the system call assembly instruction, uh, operating system knows the number for the system call, and it will execute corresponding system call. And after the system call is executed, the control is written back to the user process to continue execution. Note that when the system call is actually executed by the operating system is actually running in privilege level that is indicated by the mode bit. So when mode bit is 0, the processor is in privileged mode. When mode bit is 1, the processor is actually running in non-privileged mode. And at software level, the way system call works is when we do the system call, like when the user program does the system call, at kernel level, it knows the system call number and corresponding parameters. It will check the parameters to see that the parameters are valid. Once the parameters are valid, it will call the corresponding system call code, and the system call might call the corresponding utilities. For instance, open system call might actually call various utility functions that deal with opening a disk or reading a disk. And then once the system call finishes, the control is written back to the user program so that the program can continue execution. So as I mentioned before, lab one would be you writing um, the system call. Basically, you'll be adding a new system call called get PID, which basically gets the process ID of the current process. Now let's look at interrupts. So as I mentioned before, at the hardware, we have various components in the hardware. Now, when the hardware has to communicate with the processor, there should be a mechanism for the hardware to communicate with the processor, right? So, but these the these events at the hardware happen at different points, so and we cannot predict when that events can happen. For instance, we cannot know when user presses mouse. So when user presses mouse, so an event or some signal needs to be sent to the processor, right, to notify that user has pressed the mouse. So this is actually the point of interrupts. So interrupts actually facilitate this kind of communication. So how do the interrupts get handled? Like, so how do, like, interrupts are actually unexpected events, right? So uh, we have code executing properly and unexpected, like we have a mouse click done by the user, which is completely unexpected. So how do we handle unexpected events? So there are two basic ways. One is polling. So constantly look for events, right? Constantly check if user has pressed the mouse or not. Constantly check if user has pressed the key or not. That's one way to do it. The other way is through interrupts. So what that means is whenever user presses a button, we actually get notified through some way. So that way is called an interrupt. I mean, depending on the cost of polling, interrupts may be more efficient, or interrupts may be less efficient depending on the polling cost. If, for instance, if polling takes less time, I mean, like if continuously checking for events, if it takes less time than actually the processing needed to service interrupts, then maybe polling is better. So, as I mentioned before, interrupts is a way for operating system to take care of unexpected events. So it also provides a mechanism for a mechanism to coordinate between multiple concurrently operating units, for instance, processor and a keyboard or mic, right? So processor is communicating, processor is actually executing some code. At the same time, mic or a camera is actually capturing the video and processing the frames and sending the data to the processor. So an interrupts provide a way in which these multiple independent components can communicate with each other. So, and these interrupts are usually forced by hardware. For instance, when we press a button on the keyboard, like an interrupt is actually raised, and it's forced by the hardware so that the processor can actually service or handle the interrupts. There are two types of interrupts: hardware interrupts and software interrupts. So hardware interrupts are the interrupts generated by the external hardware, like a keyboard, like network card, so on and so forth. So, and these are called asynchronous interrupts because we cannot predict when the interrupts can happen, and they can happen at asynchronously, basically, like they don't happen corresponding to the instructions or the execution flow of the program. Whereas other kind of interrupts are called software interrupts. These are also called traps or exceptions, and these are synchronous interrupts. By synchronous interrupts, I mean, so we know exactly when software interrupts can happen. That is after an instruction gets executed, right? So we can always check for software interrupts after executing each instruction. Whereas hardware interrupts or asynchronous interrupts, we cannot know when the exception can happen. However, software interrupts, we know when the exception can happen. It can only happen after an instruction. So for an example of software interrupts is a system call. So when a system call instruction gets executed in the user mode or user application, so a software interrupt gets executed, and that software interrupt actually uh, is one responsible for transferring the control to the operating system so that operating system can service the system call or like handle the system call. So this is a primer from ECE 437 digital design course. So so how interrupts are handled, if you remember from that course. So when an interrupt comes, when an interrupt arrives, so all the other interrupts are disabled, and the corresponding the address of the instruction that is getting executed will be saved, and interrupt will be the control, like the processor goes to the interrupt service routine, and interrupt service routine will process the interrupt, and then the saved state of the processor is restored, and the execution continues with the original flow. So we have various interrupts. So interrupts, for instance, x86 defines various interrupts. There are, and each interrupt has a number that corresponding as a unique number that corresponds to that that particular interrupt. And x86 defines certain predefined set of interrupts and corresponding numbers. And these interrupts can be either faults or traps, or there could be aborts. So faults are the instructions that faults are the interrupt types which can be handled by the processor, whereas traps are instructions which cannot be handled. So that's why, so traps usually happen, like when the trap happens, the program counter is actually incremented. That means the instruction which caused the trap is never executed again. Whereas fault instruction will be executed again after fixing the fault. An example of fault is page fault. That means like when if you like, we'll be looking at what page fault means later in the course, but just a couple of things to remember. Trap, uh, when a trap happens, the instruction that caused the trap is never re-executed, whereas when a fault happens, the instruction that caused the fault usually will be re-executed again after fixing the fault. Faults are fixable. Traps can also be handled. However, the instruction that causing the trap is never re-executed. So, and there are x86 also provides various other numbers which which can be used to define user defined exceptions, like from 32 to 255. User can define interrupts corresponding, like custom interrupts. So this is a timing diagram of interrupt processing. For instance, the vertical lines shows IO events. So on the horizontal lines show the execution state. So yeah, at the beginning when the IO request happen, so initially IO device is idle. So when the IO request happens, after certain delay, IO device starts transferring the data. When the transfer is done, uh, interrupt interrupt gets invoked, interrupt gets triggered, and interrupt service routine gets processed, and then it returns the data back to the user process, and user process continues the execution. So here you can see that whenever after the transfer is done, an interrupt is raised, and interrupt uh, service routine or interrupt processing takes care of the data, takes care of processing the transfer data, and then giving the control back to the user process. So then most of the modern operating systems are actually interrupt driven. So you can imagine operating system as a giant loop that just busy waits, or that just looks for interrupts. So whenever an interrupt happens, it services the interrupts and then just goes into the loop. So because I mean, because that's how that's the only thing operating system has to do, right? For instance, operating system, you can imagine the simplest operating system which actually just listens for timer interrupts. So whenever timer interrupt happens, it sees that if a time slice has expired, if the time slice has expired, then it needs to context switch. Basically, it will pause a running process and it will take another process and resumes that process. That's it. You can think of simple operating system which works just by handling timer interrupts. At the same time, like even system calls, now let's add system calls. The way we can add system calls is again through traps, or again through interrupts. So whenever user process is executing, it has to, when it has to make a system call, the system call actually leads to a trap. Again, this is an interrupt. Now operating system needs to just service the system, or like handle the system call and transfer the control back to the user process. So you can see that operating system is actually a giant interrupt handler, and where interrupts are generated by the external hardware and or the user processes. So in the next lectures, we'll be looking at different OS components. So we'll start with process management next week. So as reading assignment, please read chapters 1 and 2 of Dinosaur or Comet book. Thank you.